X minus X. Okay. Now I tell you to close your eyes. You close your eyes, and I'm writing on the blackboard once again O, keeping empty space here and here. Maybe I put it in blue. Okay. And now I'm putting in this empty space plus X minus X. Plus X minus X. Or I'm putting in this empty space minus X plus X. In the first case, I just copied. In the other case, I switch the atoms. But if I cover this part, you don't know if I switched or I didn't switch. It means that the structure has a symmetry of replacing these two atoms by each other. It means that if I don't tell you anything more information, you are not able to say if the structure was switched or it was not switched. It means that these two atoms, for somebody who is watching the structure, look exactly the same. That's why this charge must be the same. So we have minus X equal plus X. From this, of course, you get 2X equals 0 and X equals 0. So by symmetry, the charge on each of these atoms must be 0. Okay, but what happens in the situation like CO from the polarized bond? This is a bit more complicated. Turns out that in this case, some, not all, some of the electron went here. So this one has more than 50%, this one has less than 50%. We usually write this like that, minus small delta plus small delta. And delta is smaller than 1, larger than 0. This thing and this thing are called induced charge. How big are these things? Usually very small. You can think that this one would be around 0.1 to 0.2. This is a usual case. Let's continue. Okay, so we have the induced charge of 0.1 to 0.2. Now, these are small things, very small, but turns out that they are very important for making something what is called dipole moments. So if you have induced charge, so molecule A with induced charge plus, and molecule B with the induced charge minus, you are defining a vector and denote this vector by Greek letter mu. And this mu is defined as delta times R, where R is the vector connecting A to B. Why dipole moment is important? Because dipole moment can interact with electric field, so with photons. And we can have all possible types of interactions of the matter and light. If there is no dipole moment and higher multiple moments, that would be very difficult to make any transitions in molecule and to observe anything. The matter would be dark. Another name for these induced charges is partial charges. Partial means it's a part. It's not one, it's not zero. It's something like that. This is the definition of partial. Good. Let's go further. We have the polarized bond. Next type of bond that we have to discuss is something what is called Donor-Acceptor Bond. In Donor-Acceptor Bond is something interesting. Both atoms give orbitals. Only one atom gives 2 electrons. Examples. Imagine the situation when we have NH3. We discussed this one. We said that the NH3 more or less looks like that. We have one atom here, one atom here, one hydrogen here, and one hydrogen at the back. And on the top of this, you have a lone pair. I prefer the spin up-down, but very often you can, instead of spin up-down, you can just see here 2 dots. They are coming from the Lewis structure type thinking. So this molecule has orbital with 2 electrons. Now let's take another molecule that has orbital but no electron. That would be the H plus ion. Now they can come close together. And what happens is this orbital and this orbital overlap, making a bonding orbital. With 2 electrons. Now each of the atom gave 1 orbital, but this atom gave 2 electrons. This one 0. This one donated electrons. Donated, it means gave money, usually. And this one is called donor. This one accepted electrons. That's why we call it acceptor. Which explains the name of the bond, donor-acceptor bond. One is giving, one is taking. Usually donor-acceptor bonds are weaker than covalent and polarized. Now, there is a serious problem here, because you can think looks something like that. N, H, 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 H. With this one being R1, 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 and this one being R2. But this is not true. The real NH4 plus molecule looks like that. This R1 and the other R1 are exactly the same. No difference between them. This is very interesting because before making the bond, this hydrogen and these three hydrogens are very different. But after making the bond, they are exactly the same. So if somebody asks you, which one is the donor-acceptor bond in this molecule, it's almost impossible to answer. Because in fact, each of the bond is 1/4 donor-acceptor plus 3/4 covalent. And now the most important part. We make a classification, but nature doesn't know this classification. It's only in our head. This is not reality. So you have to be always aware of this one. We make the classification to make thinking easier, but if the experiment shows something else, not the experiment is wrong. Usually our thinking is too simple, like it is in this case, for example. Good. There is one more type of bond left that we didn't discuss yet. Well, we discussed, but we didn't put in the classification. And some people don't put it in the classification. Well, I write it as two separate. One is the hydrogen bond. And the hydrogen bond most usually is a donor-acceptor bond between H atom and oxygen atom. Example, water dimer. If you have one water molecule, there is a covalent bond, in fact covalent polarized bond between oxygen and hydrogen. And if you take another molecule, there is another such bond here. Hey. But if you think about that longer, in fact, the oxygen atom has two lone pairs. So what I prefer to do, I prefer to write this structure in a different form. Namely, I put one lone pair here, another lone pair here, and there will be one hydrogen up, one hydrogen down. Similarly, I can write here, but this type, I just keep the hydrogens inside the plane, and the lone pair would be difficult to write lone pair in 3 dimensions. Okay, and now you see where the bond is happening. The lone pair of the oxygen making a bond with the hydrogen orbital, like that, donor-acceptor bond. Hydrogen doesn't give an electron. Hydrogen already gave all the electrons to this bond, making one molecular orbital. Now hydrogen makes the other molecular orbital in this direction. So this is the hydrogen bond. How do you think the distance here and here? AB. Okay, think, I come later. Equal or not equal? We have two distances. This hydrogen is bonded to oxygen, and this hydrogen bonded to this oxygen. So now in the NH4 molecule, the distances were the same. Now I'm asking if this distance and this distance is exactly the same or not? The same A, not the same B. B. A. Two A and the rest B. Turns out it's B is the correct answer. Now I tell you how people found it. This is difficult to find, very difficult to find, to be honest. Right. If you have H2O, we just said a moment ago that oxygen, hydrogen, hydrogen, and two lone pairs. You can imagine that this one reacts with H+, and if it reacts with H+, it gives a structure that looks like that. H, 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 plus. And that one looks exactly like ammonia, like NH3. Now, these bonds R, and R are exactly the same. Well, according to what we wrote, this is the bond between hydrogen and oxygen. This is a hydrogen bond. And now they are the same. So let's take this molecule and connect this molecule with one more molecule of water. If we connect it with one more molecule of water, that looks like that. O, H, H, O, H, H. And of course the bond I'm drawing now, it's above the plane like that. But I'm drawing it inside. So it would be hydrogen, hydrogen. This is a very similar situation to the situation here. We have two oxygens, we have one H between them, and I just attached one extra H to everything, and the charge is plus. So very similar situation. And now the question if R1 and R2 are the same. And we already know they are not the same, and that was your intuition, the same. Now, how people know they are not the same? Turns out that this hydrogen, it doesn't matter. It can be here, or it can be here. One closer to this or closer to this. So you can write a potential energy map for traveling along this axis. This is R, and that will be the R. Of course, if the hydrogen is very close to oxygen, the energy is high. The same happens when the hydrogen is very close to oxygen on the other side. Now, if the distance is exactly the same, the plot would look like that. Minimum would be symmetric. If this plot is symmetric, then you can see vibrational levels like that in experiment. Okay, so if you make experimental spectrum, light, wavelength, and here is intensity, the plot would look something like that. Where this distance between these two peaks is exactly the same like distance between these two peaks, these two levels. Okay? This is the experimental spectrum. Now, turned out that the experimental spectrum looks very different. That the experimental spectrum looks like that, but just next to it, there is another peak. Another peak, very close, very close, very close, very close. So always they come in pairs. So this is wrong picture. Turned out the correct picture looks like that. And then you have one levels here and another levels here, energy levels. And now these two levels, they can interact with each other, making each of them double. And giving this spectrum. So to find that this distance is not the same, that it can be here or here, it means closer to this oxygen or closer to this oxygen, takes pretty it requires very complicated experimental technique to find it, and a lot of thinking. Maybe it's time for a break, isn't it? Yes, it's even 5 minutes too long. So we make 10 minutes break, and then we have just 20 minutes of class. Thank you. Good, we have few things to say. First one. No, there's one more bond to discuss. Well, again, bond, not bond. Some people say it's bond, some say it's not. I'm in the van der Waals bond. If the class is not recorded, maybe I write bond, but since the class is recorded, I just write here van der Waals interaction. Because it's not really a bond. Similarly, like ionic bond is not really a bond. So we have van der Waals interaction, and we discussed it before, and I think this one is closing our classification of different types of bonds. Now you should be able to give example of each type of bond. So a solid or a molecule that is realizing a given pattern of bonding, which I believe is not very difficult. Good. We have a few things to explain. First one is partial charges story. Come back. We have a molecule that one atom has some small positive charge and another one has small negative charge. So we have the partial charges or induced charges. And we have another molecule, C, D, with Xi plus, Xi minus. One day you have to learn all the Greek letters. This is Xi. You know alpha, beta, and so on. This is just Xi. Next one. Anyway, you have Xi plus, Xi minus. And now somebody is asking you, is delta larger than Xi or not? Or Xi is larger? How to answer this question? To predict how large the partial charges are, people introduce the idea of electronegativity. That's a long word. Electron from electrons, negativity from being negative, so having negative charge. What is this? This is strength of a given atom to pull electrons. Again, pull means bring. Push, take away, pull, bring together, right? So now you can imagine that every bond, like A and B, consists of two atoms. One of them is pulling electrons, and the other one is also pulling electrons. If they have the same electronegativity, then the pulling is the same, and each of atom takes 50%, 50%, and we have covalent bond. So if we have the same electronegativity, we have 50-50. But now, if one of the atom can pull stronger and the other one can pull only weaker, one takes 70%, one takes only 30%, and we have polarized bond. Okay? So now electronegativity is a number for each atom between 0 and 4. I don't remember the exact values, but let's check. You can see it in figure 2.12. If somebody has a book, please open on 2.12, page 73. And you see that the highest electronegativity is the fluorine atom. F equal 4. And usually people denote it by the Greek letter chi. Again, Greek letter. Electronegativity of the fluorine atom is 4. It's the highest possible. The next 2 is the electronegativity of oxygen, and which is 3.4. And if you take periodic table of elements, the highest electronegativity is here in the fluorine atom, and the lowest one is there. So that's the idea to remember. Atoms that are here have very little power to pull electrons, but highest power has fluorine and atoms around fluorine. What is a good part of knowing electronegativity between atoms? You can solve some real problems. For example, if they ask you, if pH3 or NH3 has more polarized bond, the way of solving this is just checking the electronegativity. Electronegativity of phosphor is equal to 2.2. Electronegativity of nitrogen is 3. And electronegativity of hydrogen is 2.2. You see that in this case the difference of electronegativities is 0. And this case the difference between electronegativities is 0.8. So we get that pH3 has almost covalent bond because H and P has the same pulling strength, but by NH3 the bonds are polarized toward the nitrogen pulling stronger. Now, next thing, electronegativity is nothing real. It's only in our head. It doesn't exist. Nature doesn't know about electronegativity. So, if nature doesn't know about electronegativity, we cannot measure it. So, it must be defined. And the definition of electronegativity is when this one is ionization potential, and this one is electron affinity. And you should remember these two names when we are talking about atoms. Ionization potential is how much energy you need to take away one electron. And electron affinity is how much energy you get when you put to the atom one electron. So this is the most often used definition of electronegativity. Another one, difficult word. Polarizability. Okay. What is polarizability? In the case of electronegativity, it was the power to pull. In the case of polarizability, somebody is pulling me. If I go very easily, I have high polarizability. But when I don't want to go, I have very low polarizability. So you can imagine that this is equal to softness of electron cloud. Again, now we should think when the electron cloud is soft and when it is hard. Any ideas? When the electron cloud is soft, for which type of atoms? Okay, if I have one atom here and the electrons are here, and I have another atom here and the electrons are here, in this case they are very close to nucleus. So they are strongly attracted. If you want to take it away, you have to take it away from the nucleus. So in the case of the small atoms, or small ions, this is also small polarizability. Now, in the case of the large atom, when the electron is here, it's already far from the nucleus. It's kind of easy to take it away. So this cloud is rather soft. Small cloud is hard. So large cloud, large atoms or ions, they have large polarizability. Now, which atoms are large, which atoms are small, or which ions are small? You remember that we are drawing for atoms. We said that the largest atoms are here, smallest are here. So this is the plot, how the polarizability grows, more or less to remember. These are the largest atoms, these are the smallest atoms. These are for atoms. What about for ions? Well, if you have cation, it means you had big atom with a valence electron and you removed it, making cation. So this one, the big electron, the large electron is gone, keeping only the chemical core, making it small. So cations are small and they have small polarizability. An ion, you put another electron here. this becoming even larger. So anions are large, and they have large polarizability. Okay, now we define something what is called formal charge. Number of valence electrons minus number of lone pair electrons minus 1/2 of bond electrons. Let's calculate formal charges for atoms in different molecules. Let's start with our favorite, with water. The water has 2 lone pairs. Hydrogen has no lone pairs. Let's do. The formal charge of hydrogen would be equal 3 atom valence electrons. Hydrogen has 1. Minus number of lone pair of electrons. Hydrogen has no lone pairs. Minus 0. Minus 1/2 of the bond electrons. Hydrogen has 1 bond. The bond has 2 electrons, so we have minus 1/2 times 2 equals 0. What is the formal charge of oxygen? Let's calculate. Number of valence electrons in oxygen. How many oxygen has valence electrons? 6. Okay, let's go further. Minus number of lone pairs electrons. 2 lone pairs, every lone pair 2 electrons, so minus 4. Or maybe to write it more clearly, minus 2 times 2. Minus 1/2 of bond electrons. 1 bond, 2 bonds. 1/2 times 2 bonds means 4 electrons. 2 times 2. Which gives 6 minus 4 minus 2 gives 0. Boring. Boring topic. We found that the formal charge on hydrogens is 0, 0, 0. When it's not clear if it's O or 0, this denotes 0. Okay? So why people introduce formal charge when for molecules turns out that everything is 0? The formal charge sometimes helps when you have strange molecules.